Alright, now I can start by defining the material. So you go to define parameters. The first one is alpha. Okay, so what is alpha? Alpha has to do with the direction of the load to grain alignment. Okay, so you can either insert 0 here or you insert 90. You can see when you insert 0, that means the load is parallel to grain. When you insert 90, that means the load is parallel to grain. Perpendicular to grain. Okay, so but how will you know if the load is parallel or if the load is perpendicular? You have to check clause 6.1 of Eurocode 5. Okay, so I have that opened here already. Okay, so this is clause 6.1. You can see this is design cross section subjected to stress in one principal direction. But before we do this, let me just give a simple explanation. You know, a timber is different from other structural elements. For example, concrete. Okay, when you want to test for the compressive strength of the timber, you can test it in two directions. One, you will test it parallel to the grain. Also, you can test it perpendicular to the grain. Okay, let me show you a picture. All right, so this is a picture. You can see this is the grain of the timber. This is a timber. All right, you can see the direction of the grain. You can see the grains. This all this arch we are seeing on it, that is the grain. All right, when you see a timber, definitely you see a particular grain on it. So the direction of the grain is not just there, it has impact on the timber. Okay, so when you want to test it, you can test it in two directions. You test it parallel to the grain. If you look at this is parallel to the grain. You can see the load is parallel to the grain. All right, so that's what you have here, compression parallel to grain. Also, you have this, you can see that the load is perpendicular to the grain. Okay, so you test it in these two directions. Okay, now you can go back to the code. Now the code has something to say concerning that. The clause says that you can see clause 6.1 applies to straight solid timber. That's exactly what you have. So to straight solid timber, glued laminated timber, or wood-based structural products of constant cross section. All right, then it says the grain runs essentially parallel to the length of the member. Okay, so if you look at the diagrammatic expression they have here, you will see that this is the direction of the grain. This you are seeing in direction 1. You can see this one-way direction. That is the direction of the grain. Okay, so now this is what the clause has to say. It says that the member is assumed to be subjected to stresses in the direction of only one of the principal axis. You know, you will test it in two directions, just as I said, but just only one direction will it be subjected to stress. Okay, so now we want to know if it is the direction parallel or if it is the direction perpendicular, and that is exactly what Staad Pro is asking us. So if it is parallel, it wants us to insert 0. If it is perpendicular, it wants us to insert 90. Okay, so let me go to the code. First of all, we have tension. Right now I don't have anything to do with tension. If you are designing for a roof truss, you know, in roof truss you have your trusses, you have some members in compression, you have some member in tension. Then we can be concerned about tension, but for now that I have frame, everything is in compression, so I'll have to consider this 6.14 and 6.15. Now let me confirm if the compression is parallel to the grain. If the compression is parallel to the grain, this expression has to be satisfied. This sigma, it stands for what? The design compressive stress. Design compressive stress. And as we checked during the analysis, the maximum we had was I think 9.5, or is it 11.5? I think 11.5. I've even forgotten. I should have written that somewhere, but we can always check that. Now then again, the FCD, which is what? The design compressive strength along the grain. All right, so the design compressive stress along the grain, we got that to be 11. Let me just 11.5. I can't remember that actually for now, but I think it is 11.5. If you still remember, that's the result we checked while we were doing the analysis under post-processing. Then the design compressive strength, I gave that in the question. the design compressive strength. So we have the design compressive strength parallel. When we say parallel, that is along the grain, that is parallel to the grain. So parallel to the grain, the design strength, not stress, strength, you can say the design strength is 23. So if we now if you compare that, you will see that 11.5 is less than 23. Therefore our compression is parallel to the grain. Okay, so we can only pick one. So we can say compression is parallel to the grain. If this is not satisfied, you can also check this one for the perpendicular, but since this one has been satisfied, I don't need to go to the other expression. So let me just go to the answer is parallel, right? You can see the answer is parallel. So let me go back to Staad Pro. Then Staad Pro says if the load is parallel to grain, I should insert 0. But if it is perpendicular to grain, I should insert 90. So it is parallel, I'll just insert 0. Then click on add. Perfect. Then the DFF, which is the deflection, I told you you cannot calculate it, but I just need to know the clause. So the clause is what? Clause 7.2. So you can just check table 7.2. So let's quickly check table 7.2. Alright, here is table 7.2. Table 7.2 is a table that will provide you with the limiting value for your deflection, basically for beams. Okay, you know that when we are talking about deflection, what we are referring to is the horizontal element like beam. Okay, and then when we are talking about column, what should come to your mind is buckling. All right, so that is the limit state of serviceability for those two elements. Now that we are talking about beam, you can either have the beam as a as a simply supported, that is sitting on two supports, okay, or you have it as a cantilever beam. All right, so depending on the deflection you are looking for example, if you are looking for the instantaneous deflection, it should be between L over 300 to L over 500. Let me just take you through what those kind of deflections are. So when you check this diagram will help you to differentiate between the different kind of displacements. You can see from this particular sagging point up to this point, that is what we call the W instant, that is the instantaneous deflection. Okay, here you have the creep, that's the creep deflection. Here you have the final deflection, you have the net final deflection. If you want to calculate the net final deflection, you have the formula here. So depending on any of that deflection you want to check, this is the limiting value. Okay, this is the limiting value. So L over 300 if you want to calculate for instantaneous, but let's say I want to calculate for final, and then the beam is what? It is a simply supported beam. It means that my deflection, the answer I have to get for my deflection, Staad Pro cannot calculate the deflection as I've explained earlier. So you have to determine your deflection manually. All right, so at the end of the day, when you are done calculating your deflection, for you to know if your beam has passed the deflection check or not, you have to compare that value to what you have here, and that is what we call the limiting value. So that value is what? L over 150 to L over 300. So the value you get must fall in between L over 150 and L over 300. If it is not between this value, if it is higher than this value, definitely it has failed the deflection check, and you have to change that section. Okay, so you have to do this manually. All right, so what is L? L is the length of that beam, from the support to the support. So that is the length. All right, so this is the limiting value. The value you get for your deflection, you compare it to what you have here. It must fall in between, okay, for it to pass the deflection. If it didn't fall, then it has failed deflection check. But you will not be able to do that with Staad Pro. You have to do that manually. All right, so that is what I just want to show you about that. Then we can move on. So I'll just move away with that. Then you can go to KC90. You can also check your clause for whatever that is. You can check clause 6.15, but the value is 1 as the default. I'll just click on add, so we don't waste our time. 1, I'll just use the default. To get a particular specified answer, you can always check the clause. It will always provide you with a clause. You don't need to have it offhand. For example, this one 6.3.2. So you can just get the code and then get that. So now let's go to LDC. This is for the load duration class. Load duration class, it is medium. You can see the load duration class in the question is medium term. Okay, I believe you know what that is. Medium term load, there's short term, there's you can also check table. I'm not sure the table, but when you have the code you get that. So medium term action, click on add. Then the member type, we have beam. Let me click on this, and then I can also create for column. So column is 2. Okay, then you can also check 6.3.2 to visualize what that is. So I will assign the first one to all the beams. I will assign this other one to the column. Then the ratio to the actual permissible whatever, I'll just click on 1. That's the default. And then the service class is 2. Let's see that. The service class, you can see the service class is 2. So that should be there. Then you pick service class 2, click on add. And then the timber strength class, that's class 14. Okay, that's class 14. So just click on this drop down, then you pick class 14. All right, then you can click on add. Then we are done. Now you can close. All right, so now we need to assign them. So the alpha, I will assign alpha to everything, that is the load is parallel. So click on alpha, then you can assign to view. Click on assign to view. Then KC90 also assign to view. All right, then KY also assigned to view. KZ assigned to view. Then we have the LDC, we are assigning to view as well. MTYP1, we are assigning this to the beam alone. So let me select all the beam, click on parallel to X, also parallel to Z. Then I can assign that to selected beam, click on assigned. Then the MTYP2, that should be assigned to the column alone. Then we can just select everything parallel to Y, and then we assign that. Then the next one, ratio, assigned to view. This also assigned to view. And then the last one, which is the strength, this assigned to view. Everything is class 14. Now we need to define the command. You only have one command. Click on command. You only have one command, and that's just to check the code. So click on add and then close. Now let me assign that command. This is a command, check code, assign to view, assign. Yes. So that has been assigned. The next thing to do is to design. To design, you need to click on analyze, and then you run analysis. Save. Let's wait for it to do that. Alright, so perfect. The design has been calculated. We have 0 error, 0 warning, and 0 notes. So you can click on view output file, then you click on done. Alright. Then you can see what we have here. We have the timber design. So just click on the timber design, and then you can see all your members. So you have the member. This is the first member. You can see the result for the axial force, the moment, and then the moment in the Z. Okay. So you can see this pass. The section actually passed for this particular member. Then also this one is also passed. What about this one? Also passed. Then this other column, it's also passed. This other column pass, and then this other column pass. Okay, so the section pass, so we can go ahead and check everything. Okay, so that is the end. To get to this particular portion, you can close this. You can always come here, this start output. So when you click on start output, it will bring you back here. Okay, so that's another way to come back here if you want to. Then you can close that. So that brings us to the end of the design of a timber frame. Okay, then in the next class we will discuss a timber roof, a roof truss, where we have the load due to the purline, we have the load from the the roofing sheets, we have the load from the rainfall. So basically what we have to do there is just the difference will be in the loading and then the compression and tension member. Okay, the design will still be the same way. All right, so thanks for watching. If you like this video, make sure you give the video a like, and if you haven't subscribed, kindly subscribe to my YouTube channel. Thanks for watching, and thank you for always coming.